kind of aspiring band, you'd have to go to an expensive recording studio to record your music, and then probably push your CD out into a CD store, and hopefully some people would actually walk into the store and buy your CD there, and it has a catalog of probably about 100,000 videos. If you compare that with the music data that is nowadays available, then we're actually talking about orders of magnitude more data. Going from, you know, a catalog of probably about 1 million songs with Pandora to catalogs of over 10 million songs with known services like iTunes or Spotify or RDO. And if you would go onto MySpace, we're talking about another multiple of that of music content that is available. And every day, lots of content gets uploaded to this, gets added. That are out there, which is probably above 100 million songs as we speak. And bringing them out there, serving to the users, so that they're not always kind of listening to Britney Spears on the radio, right? That's kind of like the motivation that we have. So the question is, how do we do that? How do we find the right music? There's basically some kind of black box that will automate the analysis of the millions of songs out there, okay? And so one of the things one could do is one could think about building a black box that can automatically tag music with all kinds of tags, including genre tags, mood tags, instrument tags, usage tags, etc., etc. So the idea here would be that given a song, now instead of having a human listen to this song, we have this black box, the computer listen to that song, and then this black box is able to tell us which tags in these categories here are most applicable to that song, i.e. to that waveform. For example, here in this case, we're going to be talking about a jazz song that is romantic with some piano and good for dating, right? And for another song, this will look differently. We build such a system, and in fact, what the system does is it listens to a waveform that it has never heard before, just like a human would.
Fly me to the moon.
Basically, we feed this waveform into the system, and this is what comes out of it. What comes out of it is a bunch of tags, which are these blue words here. And what we did is we poured them into, like, you know, this black matlib here, which is just a standardized textual format in which we can then plug in the most likely genres, the most likely instruments, etc., to obtain some kind of simple summary of the music. Okay? Now here again, in this case, the computer had never seen this song before. We feed the waveform into the computer, and this is the description that it comes up with. You know, it comes up with words like jazzy, count, calming, sad. It also comes up with some words that may not necessarily be entirely applicable, like, for example, acoustic guitar. There's not much acoustic guitar in here. There are some errors. But on the other hand, if we were to feed it with a song like this one, so then it comes up with a description where it says something like dance, hip-hop, exciting, good to play at a party, versus this one is maybe good to play when hanging with friends, which is a little bit calmer, etc., etc. The bottom line here is that both of these songs were never heard by the computer before. The only thing we did is we feed the waveform into it, and this is the description that the computer comes up with. Nothing is perfect, but clearly, this description is certainly more applicable to this song, and this description would clearly be associated by everybody with this song if we were being asked to match them up with the right songs, right? So that kind of like shows us at least that, you know, building a system like this is not really completely impossible, but again, we will make some mistakes also because, you know, when humans would have to do this, they would make certain mistakes as well. But anyway, so that's the idea here. So the idea is, given a song, can we build a black box that can automatically tag it with appropriate natural language tags? And so if we do this now for, let's say, the millions of songs that are out there on MySpace, and what you end up with is some annotated or indexed database of songs, millions of songs by, let's say, a couple thousand tags here. And then you can use that database to address the problems that we were talking about before, right? For example, if you're looking for happy rock for the gym, then you can basically select those songs from the database that have been tagged with those tags and use those songs to build a playlist or a radio station. Right? That's one way to go. The other way to go may be that, you know, you want to feed the system. Oh, okay, I didn't know this slide was coming on. But so basically, this is just a quick example here that we're not only talking about this at the lab, but we're actually also doing it all the way up till the front end. So one of the things that some of the undergraduate students at the lab build is actually a music search engine where you can enter a bunch of tags in a little search box here, like for example, romantic, jazz, and saxophone. And then what happens is that as a result, you get a list of songs that are romantic jazz songs with saxophone in them. Okay, and you also get like little descriptions of the songs and things like that. But so this is the kind of functionality that I tried to explain in this previous slide here, where given, you know, a semantic query, we can now build playlists of songs that are relevant for the tags in the search query. The other thing you can do is you can actually say like, well, what if I don't really want to describe what I want to listen to with words, but I want to describe what I want to listen to with other songs. For example, I want to feed my search engine with a query song, right? And now I want the computer to generate a playlist of songs that are similar to that song. Well, you can actually use the same database for that because you could look up that song in the database, right? You could look at which tags are applicable to that song and then recommend other songs that I have similar tags associated with them and generate a playlist in that way. Okay, we also implemented a front end for that, which is the Marcovoni radio, which is actually a radio station that Brian created, who Vaslav was just talking about. And so basically what happens here is that you feed it with a couple of songs and then it starts recommending more and more songs in the radio station that are similar to these songs, but in a way that is entirely based on analysis of the waveform. And the reason why I'm saying this is because there are different services out there, of course, as we talked about before, that are looking into music recommendation, like for example Pandora. But the way that they differ, that their approaches are different from what we do, is that in the case of Pandora, they actually have an army of musical experts sitting down at their computers, ripping apart CDs and listening to songs to manually annotate them. So they do the same thing as what we do, but the difference is that while we're doing it with a computer, they are building that index database with humans, which is one of the reasons why their database is not as big yet as of present as, for example, iTunes database or our DO database of songs. I don't know the exact number, but as far as I know, Pandora nowadays has a library of about 1 million songs. Okay, also one of the things with Pandora is that if you want to seed the system, you have to provide an artist name or a song title. It doesn't mean that they're going to play that song for you, but that's the song that they're going to seed at least the radio station with, and then they're going to play similar music to you. So you have to know an artist name or a song title to start off that radio station. Another service that's out there is iTunes Genius. So basically the idea there is you upload a song to Genius, and what it'll do is it'll return you a bunch of songs that are similar to that seed song, which is basically similar to the Marcovoni radio that we developed. The difference here is the following. Let's say that tonight you go into your garage, you record a song there, all right? Put it on your computer, upload it to Genius, because you want to look whether there's other songs out there that are similar to that song. What's going to happen is this. It's basically going to tell you that it cannot find any similar songs, any other recommendations. Now, why is that? Well, I don't know why it is exactly, because Apple never tells what they exactly do. But what we suspect is what Genius does is they apply a technique which is known as collaborative filtering. And now, what is collaborative filtering? Well, collaborative filtering is a recommendation strategy where you look at how the items that you're trying to recommend have been used by a massive amount of users. For example, Amazon does something like that as well. Like when you check out, they'll tell you that other people who bought the books that you just bought also bought these other books, right? Genius is trying to do something similar, but using sales records and playlists of all the subscribers they have. Okay. So the idea here is you have this huge matrix of millions of users of iTunes by millions of songs they have in their library. And what they do is they collect some type of feedback from these users, which could be explicit in terms of star ratings, or which could be implicit, most of the time it's that, by just knowing that the user has played this song in their playlist or the user has bought this song, right? And the way the recommendation then works is that given a song, you basically look at which users have bought this song or have highly rated this song, and then what you will do is you will recommend other songs that have also been bought or have also been played by those users. And in the end, this is really like, the golden standard for recommendation, right? If two songs have been played by, let's say 100,000 listeners in common, right? Then you can be pretty sure that they're two songs that fit very well together in a playlist. The problem very often is that for a lot of songs in this matrix here, that the column is actually empty, meaning there is just no data in there because people have never bought the song or never put it in a playlist because they don't know about the song. Right? I don't know whether you know that, but like, for example, I think in iTunes, it's probably about 0.5% of their catalog that is responsible for roughly 80% of their sales. And I'm not sure about the numbers, but I think it's anywhere between 70 and 80% of the songs that just never sell a single copy. So we're talking about 80% of these columns being pretty much empty here. And therefore, again, I don't know exactly how they do it with Genius. The point is if you upload unknown songs into Genius, you're not going to get anything out of it. How can you address this problem? Well, the way to address this is by saying, well, we're not going to look at sales records, but we're going to build a computer system that actually looks at the waveform of the music, that actually listens to the music like a human would do, right? And then use that analysis to make recommendations. And of course, the waveform is available for any song, whether it's known or unknown, right? So basically, that's kind of like the story about Genius. So what we do is, how does that contrast with what Genius and Pandora does? Well, in our case, we do the annotation automatically, so not by humans. We also allow people to look by specifying what they're looking for with natural language words. Pandora in principle could do that, but they don't seem to do it. And I think the reason why they probably don't want to do it is because if they would allow it, people could reverse engineer their database, right? That may be one of the reasons. But anyway, so we allow people to look by natural language query, or we also allow people to use some type of Genius mechanism where they upload one or more seed songs, and we recommend them similar songs exclusively by analyzing the waveform of the songs. Okay, and as it turns out, in fact, a couple of years ago we did a little comparison between the playlists that are generated by our system and Genius's system on songs that Genius could make recommendations on. And as it turns out, the people that did the survey, the playlist survey that we have built upon that, they voted the both systems as being equally competitive. The one condition was that we had to hide the artist names and the song titles so that they actually were listening to the music, because otherwise, of course, in the case of Genius's recommendations, just by recommending similar artists, people would look at the recommendations and vote the playlist with most of the similar artists in there as being the one that's more relevant for them. But otherwise, those systems would find equally competitive, which is a very stimulating result in terms of using waveform analysis to make music recommendations versus collaborative filtering, right? Okay, so now how does this work? Well, the way this works is by using machine learning and signal processing. So basically what we do is, in order to make the box intelligent, we show it a bunch of example songs that are associated with a given tag. For example, for the tag rock, we show it, let's say, 1,000 rock songs, and then our machine learning algorithm will somehow try to figure out what are the typical acoustic patterns that keep reoccurring in these rock songs, and will associate that pattern with rock. And then if some future new song that it has never seen before and has that same blue pattern in it, then the system will decide that this is a good example of a rock song and index it that way. Okay, so this is how it works at a higher level. Now at a slightly lower level, how does this work? There's many different ways of making this work, by the way. We're not the only ones that are doing research on this, so what I'm telling you now is just an example. It's not necessarily the best example, it's also not the worst way of doing this. This was one of the first ways of how people started doing this 4 or 5 years ago. Given a training set of songs associated with a tag, so let's say it's given 1,000 songs that are associated with the tag rock, what we're going to do is we're going to estimate a statistical model. We're going to estimate a distribution of acoustic features that are commonly associated with this tag rock. That's what we're going to try to do. So what does this mean? Well, what this means is the following. Let's just start looking at an individual song, just for starters. So this is my song here, right? So what I'm going to do first is I'm going to take that song and I'm going to chop it into little pieces. Each of these pieces is probably about 50 milliseconds or something like that, a bit longer, a bit shorter, doesn't really matter. From each of these pieces, we will extract some information. You could extract information related to the timbre, to the harmony, to all kind of information that's available in this little piece. Very often this will be related to some type of spectral analysis, for example, extracting frequency capsule coefficients and their derivatives. There are several options for this. I'm not going to go into more detail right now about this, but so what we do is from each little piece here, we extract some information and we represent this information in some high-dimensional feature space. All right? We do this with every little piece here. So as a result of that, the whole song now is represented as a cloud of green dots in some high-dimensional audio acoustic feature space, right? And so the next thing that we're going to do is now we're going to try to characterize the shape of this cloud of points by some statistical model, whatever it is. So what we have now is we have some statistical model here that describes the acoustic content of this song. Okay? That's the approach we're taking. Now, of course, we're not interested in songs. What we're interested in is tags, right? We're interested in the statistical model that describes the acoustic content of songs that are commonly associated with a certain tag. Okay, so what we're doing now is we're looking at all songs that have been associated with the tag rock in some training data set. We're throwing all these points together. So for each of these songs, we can extract the green cloud, right? Throwing all these green clouds together, and we're doing the same thing again. we're modeling the shape of this cloud with some statistical model. And this is now the statistical model of the acoustic content that is commonly associated with the tag, in this case, rock. Okay? So that's what we're doing. Now we can do this for rock, we can do this for hip-hop, romantic, jazz, driving, romancing, whatever you want to do. In the end, we end up with a big portfolio of models that characterize each of these tags. All right? So now, given a new song that the computer has never heard before, what the computer will do is first it will chop this song into little pieces, extract features from each of these little pieces to represent this song also as a cloud, and then we can look at which of these models explains the cloud best, right? And by doing a little bit of Bayesian analysis, in the end, we end up with some kind of relevance measure for each of the tags that we have in our dictionary based on how well the corresponding model describes the cloud of points extracted from this new song. Question?
How did you pick 15 milliseconds?
Yeah, so, okay, the 50 milliseconds is, I would say, plus or minus 30, so it could be 20, it could be 100. The reason why we picked it to have roughly that length is because that's what people in speech recognition usually pick. Again, this is 5-6 years ago when we started working on this. Also, you want that number is somehow a trade-off between it not being too short, because you have to be able to extract some information, so you need to kind of like have a little bit of time behavior in that little piece. If it becomes too short, there's like no time information in there anymore. If you make it too long, then the signal becomes non-stationary over the very long time frame, and you're just averaging, you're extracting an average feature over, let's say, 2 or 3 seconds, which then doesn't pick up on the very specific details of the waveform anymore. But the short answer to your question is it's mostly trial and error. People in speech have been doing this for decades, working with MFCCs, and that's kind of like the length that they have mostly settled on, the ones that are most useful to extract rich information from the signal. Answer your question?
Yeah, I didn't realize that was the standard.
It's not like yeah, that's exactly what it is. Yeah, it's like a standard practice that has shown over years that it extracts useful information. But it's a good question because if you make it too long, you're just extracting. You're not picking up on specific details in the signal. Like there may be like a bass hit for a drum or like something that really happened in a short amount of time. And if you make it too short, then you're just extracting noise because you want some averaging to happen, right, over a certain amount of time. Question?
Do you have overlaps of these segments?
Yes, we do. We overlap them. I didn't talk about that, but that's one of the technical details that it's for. Question?
50 milliseconds sounds like it'd be too short to get information about tempo.
Yeah, very good question. I'm going to get there in a second. Thanks for introducing my next slide. Okay, let me give you the answer, actually. I'll immediately go there. So, okay, so this is just an example here, Red Hot Chili Peppers song. We have a dictionary of probably about 200-300 words here that are in different categories, including instruments, genres, emotions, and things like that. And you can see, like, you send the song through the annotation system and it comes back with, what we call a semantic multinomial, which is basically a weighting over all the tags in our dictionary as to how applicable they are to the song. But anyway, so I want to get to your question now. So basically, because these bits that we have here are only 50 milliseconds long, there are certain things that they do not capture. And in fact, to make the case even worse, describing a song in this way is not going to capture anything that plays itself out over 1 or 2 seconds. In fact, it's going to mess it up entirely. And the reason why it messes it up entirely is because of the following. Let's say that I take the same song as the one that I started from, right? But let's say that I permute all these 50 millisecond bits now, right? So I'm going to do this. Now this thing is not going to sound like much anymore, but the green cloud here is still identical, right? The shape of this cloud does not depend on the order of these bits here, right? So as a result, the way that I'm describing the song, or the way that I could potentially be building tag models, is insensitive to the order of these 50 millisecond segments. Or turning it around, the models that we're building right now are not modeling temporal phenomena that play themselves out over more than 50 milliseconds. So how do we deal with that? Well, so one of the ways to deal with that is saying, like, well, instead of building models that just look at these 50 millisecond segments here, what I'm going to do is I'm going to glue, let's say, 200 of those together into a 10-second chunk of music. And I'm going to build a statistical model of this 10-second chunk rather than these 50 millisecond segments. Now, how do we do this? Well, one way you could do this is by modeling this 10-second chunk as a sample from a temporal model, for example, a dynamic texture model, or also called Kalman filter, or also called linear dynamic system. Right? So basically, what are we looking at here? We're looking at a model that is characterized by these equations here. Basically, it's a model that has a hidden state variable here that varies over time according to a linear equation, and that is what characterizes some type of temporal dynamic in the music signal. And then for every point in time, we observe a specific timbre harmonical component or something like that that is modeled by this observation variable y here, that is the output variable of our system. So this somehow is similar to hidden Markov models, but the big difference is that the state variable here is continuous. The reason why we did it this way is because hidden Markov models are used a lot for speech, as some of you may know. But in speech, it's fairly natural to assume that there's something like phonemes that we use to produce speech, and there's only a discrete number of them, roughly. For music, it wasn't so clear that there was just a discrete number of musical phonemes, so we decided to go with a system that has a continuous state variable. That was the reason why we did that. Now, one thing here, if you're trying to model a song like this, it may not be enough to have one linear dynamical system to explain every 10-second segment, right? Because a guitar solo may have a different temporal dynamics than an intro or an outro, right? So what we did is we decided to model these songs with mixtures of these models. So what I mean with that is we're modeling a song with something that looks like this. So what is this? This looks from very far away like a Gaussian mixture model, like a statistical model with like several blobs with means and variances and stuff like that. But from close by, if you look at this, what this actually is, it's a mixture model of Kalman filters. And what we're basically trying to do now is we're trying to say that this model here generates this song in the bottom in such a way that every 10-second segment of this song is mostly generated by one of these 4 Kalman filters, by one of these 4 mixture components. Okay, and so for example, in the intro of the song, it may be mainly the green Kalman filter that is generating the temporal dynamics that we're observing, while here, into the verse or the chorus, it will be another mixture component that is generating the musical content, and so on and so on. So the short story here is that by using these models, we allow to take into account temporal information over more than 15 millisecond segments. And building models for songs, and of course, if we can build models for songs, we can also build models for tags using this. What's interesting with this is actually if you try to fit these type of models on songs, then in a fairly natural way, the segmentation of the song comes out. And this was something that we were not primarily looking for, but it turned out that this model actually allowed to do that. By just saying like, let's fit this song with a mixture model of 4 Kalman filters, if you then, after fitting the model, look at which 10-second segments are generated by which mixture components here, it actually turns out that they don't vary too wildly as a function of time. We're actually naturally segmenting the song, minus a little bit of post-processing. The question?
There's overlapping instruments and vocal at the same time. How do you model that?
Yeah, so this is a completely data-driven approach. So it'll just model that as a whole. So it's not splitting it up into pieces. So we're not doing any like ICA or source separation or anything like that at this point. So anyways, given this type of model for songs, you can now also use this to build models for tags. Like for example, for the tag electric guitar, you collect all the songs that have been annotated with electric guitar, and you do a similar type of process as we talked about before. The only reason for this slide is to tell you that it's actually a bit more complicated than it sounds. If you're trying to fit models that are a bit more complicated, like this one's here, on a lot of data. There's all kinds of algorithms that are working on the back end to make this work for hundreds of thousands of songs. And we're going to go into detail about that. Question?
How do you define the distance metric between the Kalman filters?
Can you frame your question? Like, I mean, I understand what you're asking. The answer is scale divergence. But
right. So basically, when you match one song versus this model, you have to define some distance metric between this song's feature set versus this.
Yeah, you just evaluate the likelihood under all the different models. But one of the ways that you can do it efficiently is you take the song that is being fed into the system, you model it with a mixture of Kalman filters, and then you compute scale divergence between these models.
Okay.
But you have to do it with sampling methods because you can't do it exact anymore. So let's go back to the drawing table now. So basically, what did we need to do? We needed to collect some thousands of rock songs, right? Model all these songs with the models that I just talked about, and then we're in business. And of course, do this not only for rock, but for a whole bunch of other tags as well. Now, how do we get these examples? How do we get these 1,000 rock songs? How do we get these 1,000 happy songs, dating songs, and things like that? The first approach that we tried to follow to get those was survey methods, basically Pandora techniques. Now, our Pandora people were not musical experts that lived in the Bay Area, so to speak, without further comments. But what we did is we resorted to undergraduate students from the music department. And they did a great job. So. But still, problem is that if you want to do this for, we did this for 500 songs, and this led to a data set that's actually fairly broadly used now. But if you want to extend this to, let's say, 1,000 or 10,000 songs, then it's going to cost you a lot more effort to coordinate a lot more students and also a lot more money. So at that point, we decided, like, okay, if we want to keep pushing this forward, we're not going to be able to scale this approach. So instead, what we did is we designed this online game in Facebook, which is called Herded. It's okay. What's interesting about this, I have to give you one disclosure here up front, which is that 85% of the people that were involved in designing this were engineers. So just keep that in mind. I mean, I know that the interface is not like, the most polished thing out there, but like for a bunch of engineers generating something like this, I think, But so what we basically wanted to do is we wanted to take a crowdsourcing or human computation approach, where the idea is that instead of having people play solitaire for hours, have them have fun playing our game, and maybe by doing that, they can provide us with some useful data. Right? I mean, there's other crowdsourcing approaches out there, like Mechanical Turk, where instead of trying to seduce people with something that's fun, you're trying to seduce them by paying them with these micropayments, right? Anyway, so the idea here is there's a song playing, there's a bunch of people in the same room that are all logged into Facebook. And basically what they do is they listen to a song, and while the song is playing, there's like a little game that plays in the middle of the screen here that is related to tagging that song. And so, for example, what could happen is that there's a certain song playing, and then you get a bunch of tags here that, let's see what happens now. For example, a bunch of tags that are related to genres. So basically, what the user will do is that the user will click on the tag that they think is most applicable to the song, and after they do that, what will happen is that the system will provide them with feedback as to what other people clicked on. And the more they agree with what other people voted on, the higher score they get. Okay. Now for genre tags, this may not be like the most exciting thing to do, but as soon as you start throwing tags in there, like romancing and dating and things like that, people actually really like to see what their friends vote on and stuff like that. So as a result of launching this game, it was actually not so hard to get, somewhere close to 10,000 players registered for this and collect tags from, I think, at present, roughly about 150,000 rounds of games, which certainly pushed our data set far beyond what we had previously collected from these undergraduate students. So this certainly was a success story in that respect. Now looking at the numbers, or looking at this in a little bit more detail here, so as soon as we collect data from this game, right, let's say for example 1,000 good examples of rock songs, what we do is we feed that into our black box to train it to recognize rock songs, and then that will feed our search engine, right? Now one thing that we wanted to do is we just wanted to make sure that we were making sense here, and so in order to just check that we were making sense is we trained two black boxes, one based on our game data, and the other black box was trained on Pandora data. Now it is true that Pandora doesn't give out their data, but there's some ways to mine it from the internet. There's some tags that are available through some of the web pages that they have up for some of the artists which do contain some of the tags. So what we did is we mined some of the Pandora data, trained two parallel systems with that, and then evaluated one against the other. And as it turned out, so the green line up here is pretty much like, the expert best possible performance that you may expect, which is, the performance of the system trained on Pandora data. And then the horizontal axis here is time, right? So this is when we launched Herded, and this is as time went by. And this again is performance here, with this being our target performance roughly. And so you can see as time goes by that the performance of the system trained on the Herded data creeps up and gets very close to the performance of the expert trained data, the expert trained system, which is the validation that we were looking for. Now there's something interesting to be said about this though, because if we're going to use the game to provide data to train these machine learning models here, then we may as well do the opposite as well. We may as well use the machine learning models that we have at any point in time, right? And use those to improve the quality of the games. Because if I'm going to generate a game here, for example, that has no vocals, in the soundtrack that is playing, and the question that's being asked is whether the vocals are male or female, then people are not going to like playing it, right? So, as it turns out, but that's one thing you can do. The second thing is also that you can somehow try to evaluate which models are doing well and which ones are bad, and then kind of like design games that are directed towards those tags that you really need more examples from, right? So once we started doing that, it actually turned out that as a function of time now, again, from left to right here, the performance of the herded system improved towards the expert performance roughly twice as fast. I'm not going into detail here of how we exactly did this active learning, but so really what it boils down to is that we have to look at the machine learning models that we have at any point in time, look at where they fail, and then try to collect more data there through the game. You play a couple more games, you train your models, and you do the same thing again. You keep going back and forth. And by doing that actively, you can now train your models much more efficiently with less human effort as a function of time to get the expert performance. Okay. So bottom line here is that taking this herded approach was a very interesting experience. In fact, what's interesting about it as well is that when you integrate a game into Facebook, at least at the time, now it was getting harder and harder, but you can also extract demographic information from your players. So you can find out some information as to, what do the, let's say, the higher age categories think about rock and roll music versus the lower age categories, what do different demographic things about it, and things like that. Something interesting that we found out by kind of mining that data is that when you ask females whether a song is danceable or not, you find a very high level of agreement. So it seems like they have quite a sense of what's danceable or not. You can already guess what the next statement is, right? So yeah, we checked the males as well, and that was just one big uniform distribution. So anyway, so the point I'm trying to make here is that what's interesting about having a game inherited is that you can extract some demographic information, and as a result of that, you can actually personalize this box here, and you can build acoustic models for rock music that are now tied to specific demographic subgroups as well. This is something that we're in the process of doing, so I don't really have any specific examples of that yet. But that's certainly something that Herded allows us to do. All right, so where are we at now? At this point, where we're at is that so we basically build a system that given millions of songs, allows us to index these songs with natural language words, and we can then use that to build a semantic search engine, right? For example, there's a lot of other things we can do with that. As I said before, if instead of feeding the system with a natural language query, you want to feed it with some example song and then create a radio station from that, and we can easily do that by simply matching the tags of the seed song against the tags of other songs in the database and generate a radio station that way. Now, one of the things you may wonder about at this point is like, well, why, and that's exactly what I want to say, just double checking. So why would I tag a song and then look at similar tags to build this radio station? If I have the waveforms available anyways, why not just doing the matching in the waveform domain and not worry about tagging them? Why introduce extra noise in the process potentially? Now, the reason for that is that actually, not only in music information retrieval, but also in computer vision and some other fields, it turns out that matching low-level features, like for example, low-level features in images, to make similar recommendations is often found to be not as robust and not as performant than when you first take the images, extract some high-level concepts like tags from these images, and then match the tags. And we tried this out for music, and that was actually the case for music as well. Like by just simply matching, low-level audio content in the music was not giving us as good of a playlist as when we would extract tags and then match tags, right? However, what you could do though is you could say like, well, sure, okay, there's a problem there, but it may be possible to train a computer system, a machine learning system, to actually pick up specifically on those elements in the waveform that are important to recommend similar songs and ignore other stuff. Because if you're just matching waveforms, you're not doing any of that. You're just kind of like extracting audio content and then measuring distances between these vectors, and that doesn't work as well then, working with tag similarity. But what if we can build a machine learning system that actually learns to pick up on the important components in the waveform to assess similarity and ignore all the rest? And so then we thought like, okay, let's try to see what we can do here. So let's try to learn a distance measuring between audio clips that is based on audio content, but in some intelligent way. Let's try to do some learning such that the similarity recommendations that we get out of this are actually better than just doing raw audio feature matching. So first thing you have to do there is you have to extract some audio information from these songs. So given the song, what we're doing is we're extracting similar type of features in a similar way as what I was talking about before. And in fact, in this case here, what we're also doing is we're going to kind of cluster all these features a little bit by using some vector quantization so that every song is represented by some code word histogram over 1,000 code words. And every code word is some kind of like representative audio feature, right? This type of approach is kind of randomly picked. I mean, there are some reasons why we took this approach, but there are certainly other approaches to extract audio features from songs that could be used here. This is just an example. The only thing that we're interested in here is if I extract some audio information from these songs, is there a way that I can learn what is the important audio information to assess similarity between songs? Question?
What is delta MFCC?
Yeah, so MFCC is the Mel frequency capsule coefficients. So you extract the spectrum and then you look at the spectrum of the spectrum. And the delta is that you look at the first and the second derivative as well. Okay. One thing that we also do is we do some kind of square rooting on this histogram. I can talk more about this offline, why this is believed to be a good thing to do. But the bottom line here is that we extract some audio features. That's all that you should actually retain from this slide. The big challenge now is how can we build a learning system that picks up on the audio content that is important to assess similarities between songs. Okay, so here's the idea. So you have a whole set of training data, a whole set of songs, let's say a catalog of 100,000 or 200,000 songs. If you just extract the raw audio features like we talked about in the previous slide, then you can represent all these songs in some high dimensional space again, right? And now given a query song, because that's what I'm trying to do here, right? So given a query song, I want to recommend similar songs. So let's say that this guy here is my query song, and you can rank all the other songs according to their distance to the query song, and use that as your recommended ranking, right? So what I would do is I would first recommend this one, then that one, and so on and so on. Now, since this is a training data set, I have some extra information about these songs. I have some extra information as to which of these songs are actually good recommendations and which ones are bad ones. This is just a conceptual example, but as it turns out, all these songs are actually good recommendations and all these guys are bad recommendations. I happen to know this information again because this is going to be a training data set to train my system later on, right? So if I now do this, if I implement the ranking mechanism as I just talked about, then what you'll see is that you're actually ranking or you're recommending songs from the most relevant to the least relevant one here, which is actually a mixture of good and bad hits. If you recommend songs based on distance in this space. Everybody following? All right, now so what I would like to do here is I would like to somehow learn a transformation W of this space that reorganizes the space in a way that it generates better rankings. And in fact, what this transformation is going to do is it's somehow going to define a projection between this space and that space that projects out the useful audio information, right? And throws away the audio information that's not useful to recommend similar songs. Okay? So the goal here is, given a bunch of training data for which I know, for every query song, I can pick any of these songs as a query song. I know for each choice of query song which of the other songs are relevant or not. Right? I want to make sure that I learn a transformation of the space so that the rankings that come out by doing this distance-based ranking are optimized and rank all the relevant results above the irrelevant results. How do we do this? Well, the way we do it is we formulate this as a machine learning problem where we learn the distance between the audio representations of the query and any song in the database as a Mahalanobis distance. So these, the Q and the X are the features that we extract, the audio features, and the W is basically the transformation that we learn, right? Now, okay, so how do we do this? How do we learn this W here? So this is where it gets a little bit more technical. There is no I'm just gonna, apply some, simple learning technique here. It's actually a little bit more challenging than, like, for example, a classification problem, because dealing with rankings is dealing with combinatoric objects. And optimizing combinatoric objects can be a little bit more challenging than optimizing, for example, a classifier. Before I tell you how we're addressing this problem, one quick thing that I need to tell you about is this yellow box here, how do we get this information? How do we know for a given query song in our training data set which ones are the relevant ones and which ones are the irrelevant ones, right? The way we do this is we're actually using collaborative filtering data here. Because remember, if we have collaborative filtering data available, it's pretty much the best data to go from to make recommendations. And basically what we're doing here is we're going to define the similarity between two songs A and B as the number of users that they share. Make sense? Now, of course, that means that we have to have user information about these two songs. So what we're going to do is we're going to constrain our training data set to a set of songs for which we have passive listening information. In our case here, we're mining that information from Last.fm for roughly about, I think, 5,000 or 10,000 songs over 300,000 users. Okay? So we define the similarity between two songs in our training data set as the number of users that they share, normalized by, of course, the total number of users for each of the songs, some type of popularity metric. And so, of course, there's many different ways that we could define what is relevant and irrelevant for a given query song in our training data set. But what I think is nice about using collaborative filtering similarity is that, number one, it's certainly a similarity measure that most people would agree on is very relevant. Again, if 10,000 people share these two songs in their playlists, they're probably good recommendations for each other. You can passively collect this data, and also you avoid any type of subjective discussions about genres and things like that. Sometimes people say like, well, you can define similarity by just looking at genre tags. If those both are rock songs, they're similar. If they're not, then they're dissimilar. And then you get into the whole discussion as to like what exactly is a rock song, etc., etc. And it turns out that this actually works well in practice as well in some other experimental frameworks. But now back to the technical side of the story here. So we have our training data set. We have defined how we define similarity between all these songs in our training data set based on the Last.fm collaborative filtering data. So now we have to somehow learn this transformation to arrange these songs in that space in such a way that it leads to good recommendations. Or differently said, we have to learn which audio features are important to recommend songs and which ones are not. To do this, we use something that is called structural SVM. Now, SVM, or support vector machine, is a fairly well-known, or very well-known, in fact, machine learning technique for classification. Now, how many here have heard of support vector machines? Okay, cool. Very good. So what we're doing is we're using some type of extension of the support vector machine. In a support vector machine, you're given some description of a data item, and you're trying to predict whether it is black or white, right? Class +1 or class -1. Here in this case, it's a little bit more complicated. The structural SVM will allow us to provide an input into the system, which could be a query song, for example, and as the output provide something that is much more complicated than just a binary class label. It could be a multi-class label, membership to one of 10 classes, or it could even be a ranking, which is what we're after specifically here, a ranking of all our songs in the training data set, right? So going from SVM to structural SVM means that now we can predict with structural SVM much more complicated output structures. How does this work? Well, if you remember, an SVM learns some vector W, right? And then it multiplies this W with the description of the input for which I'm trying to make a prediction. And then once it computes that inner product, it'll basically threshold the inner product to see whether it's positive or negative and make a decision as to whether that input belongs to one class or the other. Here in this case, the same thing happens. We're going to learn some vector W, but now instead of multiplying it just with a description of the input, we're going to multiply it with a feature map that measures the similarity between my input Q and any possible prediction Y that we could see at the output of our system. A little bit more complicated, and the way that the prediction is done is by maximizing this expression with respect to Y. So basically the Y that maximizes this expression is the Y that's going to be predicted for a certain input Q to the system, right? Now you may say like, well, that's kind of like a difficult way to do prediction because now I have to optimize over all possible rankings here given an input query to figure out what's the good ranking of all songs given, an input query. It turns out that for some choices of this psi function here, there's some simple ways to do this optimization. For example, by ranking all the items in my database according to some inner product function, W transpose phi, where this is some type of similarity function between the input query and any other item in my database. Now, this is getting a little bit too technical. The high-level message here is that instead of using SVMs, we can use these structural SVMs that allow us to predict rankings. And what's core and central to this algorithm is this type of inner product between a vector W that is learned during the training process and some feature map between input queries and output rankings. That's the most important part of the message here. For the rest, everything looks identical to normal support vector machines. What we do is we impose some margin constraints to say that good results should be leading to higher scores than bad results, right? Because remember, it is what maximizes this expression here that's going to be our output prediction. So basically, similar to the margin constraints of a regular SVM, we're going to say that good rankings have to lead to a score that is much better than the score for bad rankings with some margin delta, which depends on how bad the bad ranking really is and some slack variable here. And then if we take these constraints and we throw that into an optimization problem that looks very much like the standard SVM optimization problem with some regularization term or a margin term here and an error term, then basically we have the formulation of a structural SVM. In summary, this thing, solving this thing here allows us to build a support vector machine that can predict rankings instead of binary class labels. Okay? Now, why am I talking about this? Well, the reason why I'm talking about this is because you should remember one thing here, which is this type of inner product between some W and some interesting function between the query and the ranking. If we just remember that part, and we go back to the problem that we're trying to solve, which is optimizing this W transformation matrix here to learn this Mahalanobis distance between sums, then we said that what we would do is we would rank sums by sorting them in descending order by the negative Mahalanobis distance, right? Ranking by increasing distance or, ranking by decreasing negative distance. If you look at the expression for the distance here, then you can actually do a little bit of matrix algebra on that. And you could write it as a trace of the matrix W times this expression here. As it turns out, the trace is known to represent an inner product in matrix space. This is a matrix here, and as it turns out, this is a matrix of rank 1, which depends on the input query and any item in my database that I want to rank. So basically, if you look at this thing here, it actually describes to me an inner product between a matrix W and some function between the query and the items in my database that I'm interested to rank. So the only message I'm trying to give away here is that the structural SVM framework, which uses a score function that looks pretty much like this but works on vectors rather than matrices, if we can extend that framework from learning a vector W to a matrix W, then we can actually apply it to learn the optimal transformation here. Okay, I'm putting a lot of math under the carpet, but I hope that two little bits kind of came through here, which is one, structural SVM is a very interesting framework to deal with prediction problems that are using more structured outputs than binary class labels. And as it turns out, we can use this framework here if we extend it to matrix algebra rather than vector algebra to learn transformation that we're interested in. And without going into any further detail, this is how it looks mathematically. Doesn't really matter at this point. The only thing I want to say is that it actually allows us to optimize rankings according to a whole suite of typical ranking loss functions that are used in information retrieval. Not only area under the curve, but also things like MAP, NDCG, which a lot of search engines try to optimize, precision at K, etc., etc. So that's one of the nice things. So a lot of these combinatoric ranking losses to optimize rankings can actually be plugged into this problem, and we can still solve the problem in reasonable time, because what we're going to do is we're going to use a cutting plane technique to solve this problem for a subset of the constraints. Because as you remember, what this constraint says is that every good ranking has to have a better score than every bad ranking. Of course, there's exponentially many of those, right? And so what we have to do is we have to somehow kind of cut that exponential set of constraints down to a smaller set. And hopefully by solving the optimization problem with the smaller set, we get still the optimal solution. That's what the cutting plane technique will do for us. We have also moved beyond this in many different ways to try to solve this problem. Is the battery gone? Okay. Should I? Okay, if you could just speak louder. No, I can. Okay. So let's see, where was I? So anyway, so this is the optimization problem. You solve this, and boom, comes out W. Okay. So now the question is, does this really help us? by solving this mathematical problem, getting out W, and basically extracting the audio features that are important to assess similarity. Okay, what are we looking at here? The green, so on the vertical axis are different approaches. The horizontal axis is performance, where this is low, this is high. Okay? The green approaches here are approaches that use tags. Remember, that was our original technique, right? The blue approaches here are approaches that use audio features. Now, the approaches that are circled here are the two approaches that use tags and audio features without any learning. So just raw distance between tag vectors, raw distance between audio features. And as you can see, assessing similarity between songs based on tags does better than assessing similarity based on raw audio features. This is just less robust, more noisy. However, if we do learn which are the most relevant features to assess similarity based on the framework that I just presented, then the order between these methods turns around. Both methods improve performance, which is a good thing. We're learning something. But in the case of tags, the performance increases to a level that is lower than the performance that we can get by optimizing the audio features to assess similarity between songs. Okay? So initially we thought that we couldn't really improve using raw audio features, but then by designing this technique here, we found out that using this learning algorithm would allow us to use audio features to build, for example, a radio station that gives us higher quality recommendations than using these tag vectors. Of course, then now the question is, how can you still improve on what we have? Because as you can see here, there's still a nice bit to go here to get all the way to 100% performance. So one of the ways that you could possibly think about improving this is by looking into nonlinear transformations. The transformation we looked at right now was just a linear multiplication with a matrix W, which is basically equivalent to saying that I'm going to take my data, I'm going to project it with a projection matrix N, and then I'm learning the inner product matrix of that projection matrix N. Pretty much what I'm doing. But what you could also do is you could say, like, well, instead of doing the projection of X directly on X, I'm first going to map my data into some high-dimensional feature space in some nonlinear way, and then learn the projection from that space. That's something that people typically do in kernel-based learning methods. So that would allow us to look into nonlinear mappings, for example. But one other thing which I think is actually much more promising to try to improve the performance of the system is the following. Oh, is that me?
Yes, that works fine.
Oh, yeah. I thought somebody was doing something upstairs. Between songs, right? We talked about using these audio waveforms here. The question is, how can we improve things? Well, one way that we could try to improve things is, instead of using just that, or instead of using just that, why don't we use both of them? Why don't we use N, the waveform, and the tags? That would be one possible way to try to improve the system, right? Now, in fact, there is one more step that we could very easily consider as well, because as it turns out, most artists that upload songs to their MySpace profiles, for example, as unknown as they are, most of the time there's a couple pictures there. Most of the time there is some people that they're related to on MySpace, and some other information possibly like their biography. So the bottom line is that most of the time, even for the very unknown songs, there is some extra information available about those songs, like social connectivity, like videos, images, or things like that. For the slightly more well-known bands, we may have some information on a weblog, etc., that describe the songs the artist generates. The bottom line is that often we have other information available than just the waveform, so why not use it? Okay? So the idea here now is, how can we use all this information together to improve music recommendations? And in fact, not just using other content than audio content could help us, but possibly also exploring other audio features would be a very obvious way to try to improve this system. I didn't talk much about that, but as I said to you probably about 15 minutes ago, the audio features that we're extracting here, they're not entirely random. I mean, they're audio features that have proven good performance for music, but they're also far from, the optimal choice. So how do we do this? How can we somehow use all these different variations of features and content modalities now to improve music recommendations? Well, somehow you may say, like, well, we can do the exact same thing as what we did before. Rather than just extracting a vector of audio features, now we're going to extract a vector of all kinds of audio features and visual features and all kinds of stuff, and we're going to run the same machine learning algorithm, right? But the problem is that if you do that, you'd ignore the fact that these different features actually live in different feature spaces, that they may be normalized in different ways, that some of them are visual or ones are audio features. So it's actually better to represent all these features into different feature spaces, and then initially at least deal with these different feature spaces independently before throwing things together. Okay? Now one of the ways, of course, to do this is by just ignoring my suggestion here and just say I'm going to concatenate everything and go from there. But again, as I said, that has certain dangers or risks related to it, so we're not going to do that. Instead, what we're going to do is we're going to learn weights for each of these feature spaces, and that'll help us to basically downweight the feature spaces that don't contain very useful information and upweight the feature spaces that do contain useful information. Okay? And there's different ways that you can formulate this as a mathematical learning problem. One of them is by appealing to this kernel-based learning framework, which then results in something that's known as multiple kernel learning. I don't have time to go into detail about this here, but this is pretty much the gist of what this does. It weighs individually different feature spaces depending on their relevance to the learning problem, here in this case, music similarity. But of course, one thing you may say is like, well, if I'm just going to learn one weight for each of these feature spaces, I'm either able to collapse them or upweight them, but that's all I can do. It may be that some part of this feature space is useful and another part is not. And so I'm not capturing that type of information. So instead what we can do is, instead of learning weights for each of these feature spaces, we could learn projection matrices for each of these feature spaces individually. So basically what we're doing now is instead of what we did 10 slides ago, which is learning one projection matrix for one feature space, we're now learning multiple projections for multiple feature spaces in parallel. And hooray, hooray, it turns out that mathematically we can formulate this as a problem that can still be solved in polynomial time, which is a good thing. All right, so setting here is we learn multiple projections for multiple feature spaces, and these different feature spaces are related to different audio features, to visual features, and all kind of information that we may be able to extract to do music recommendation. Does this improve things or not? Well, I can't really tell you yet because we're still implementing this. We have implemented it for some related problems, a related music recommendation problem where it did improve the recommendation last year, and also several problems in computer vision related to object recognition. Okay, the reason why we started solving these type of problems is because the data was just a little bit more easily available than the music data I just talked about. So currently, we're trying to use this on music data, and hopefully it'll improve recommendation. Now, to just stop now with a very kind of futuristic view about how I see that music recommendation may evolve from here is the following kind of use case. So we have this person here that would like to listen to some music, and so they go for a run, they would like to listen to a certain type of music. They still have to either use a search engine and type in what they want, or they have to provide some seed songs to generate the playlist that they may be interested in, right? What I'm thinking is that to really build a system that people will use at a much larger scale, we should try to avoid all of this here, because some people are not very comfortable with typing in what they want, and some of them don't actually have much music on their phone that they could use as a seed song as they're about to take off for running. So the idea here is could we possibly automate this? Could we possibly allow the system or build a system that doesn't require any clicks from the user? One of the ways to do that would be to look at a whole bunch of the sensors that are available in smartphones and try to use these sensors to figure out what the user is doing or how the user is feeling, and basically adapt the radio station to either the activity or the mood of the user in a dynamic way so that you don't require them anymore to say what they feel like listening to or provide seed songs. You may say like, well, okay, that's kind of an interesting idea, but this is going to be a heck of a job to implement this, right? Now, as it turns out, interesting, this phone has, let's say, 20 sensors. Each of these sensors generates a signal, right? Now, each of these signals is what? It's a one-dimensional time series. So, oh, wait a sec. We have a black box that can automatically annotate one-dimensional time signals, right? So we can actually use the music annotation machinery now to automatically annotate sensor signals from the phone. Of course, it doesn't really make sense to annotate these sensor signals with genres and things like that, so we're mostly focusing on emotion tags and usage tags now. But once we've done that, once we have used these algorithms to automatically annotate the sensor signals from the phone, with usage tags and emotion tags, we can then match those tags against the tags that we have for the songs in our database and recommend the songs that are hopefully good matches for what people are feeling or doing. Of course, you could also even think like, yeah, why not, kind of associate genre tags to these accelerometers as well.